or we started with sets and ended somewhere. And the idea is to continue today or to finish it today. We don't have too much to do under sets. We said set is what? A well-defined collection of objects of the same kind. So if it's not well-defined, it's not a set. If it's not of the same kind, it's not a set. We looked at the finite sets, we looked at the infinite sets, null or empty sets, unit sets, then subsets. We also looked at universal sets. We talked about the equal sets, equivalent sets, disjoint sets, and now we are going to the demonstration. So we have two sets problem. So listen to this. Thank you. Listen to these various subgroupings we have. I'll start with the U. U is the universal set. People are still now joining. Just a minute. Okay.
Yes, sir.
Thank you. So I was saying last week we talked about universal sets. We cited examples like students of Nyakote, farmers. We have the subsets. We talk about traders. You can have traders, you can have maize traders, you can have vegetable traders. Vegetable itself can be a universal set where we have the various vegetables under them. So once you hear what is being described, if you are not given the universal set, you will have to find out how that universal set is. Now, so the U you are seeing there is a universal set, and the 20 in the bracket tells you that there are 20 elements in the universal set. 20 elements in the universal set. And this universal set has two subsets. The first subset is A, that has 10 elements. The second subset is B, that has 12 elements. So everything within the rectangle, the big rectangle, when you add all, we are getting a 20. Now, we have 6, we have 4, making 10. We have 8, making it 18. Then we have 2, making it a 20. These are the figures we add to get the universal set. At any point, any of these numbers can vanish, and you'll be asked to find the missing value. So if 4, for instance, is not there, how do we get a 4? We know that when you add 6, 4, 8, and 2, you're going to get 20. So if 4 is represented by X, all you have to do is to add 6, 8, and 2 which gives you 16, and subtract from the 20, then you have the value of your x, which is the 4 we are seeing there. The 10 you are seeing against the A tells you that if you add everything within that ring, the oval on which the A is sitting, if you add everything within it, it should give you 10. And the numbers we have there are 6 and 4. When you add them, you are getting your 10. B, it has 12 elements in total. So it's telling you when you add every figure within that oval named B, you should be getting 12. So when you add 4 and 8, you're going to get 12. Now, all these things have special names. The 4 we are seeing tells you that there are 4 elements in A that also belongs to what? B.
Hi.
There are 4 elements in A and they also belong to B. The 6 tells you that there are elements that belong only to A. Only to A. They belong only to A. Exactly A, nothing else. The 8 is saying these are elements that belong to only B and nothing else. Now, the 10, get the difference between the 10 and the 6. When we ask for how many elements are in A, how many elements are in A, that one means we should add everything along the ring A. But when we say how many elements belong only to A, that is 6. The only is bringing the difference. Only mean strictly A, they don't belong anywhere. So we are not going to include the 4. Let's say, for instance, you have diabetic patients who are also hypertensive. So the A you have, let's say the A is the diabetic patient, the B is the hypertensive patient. So those who have diabetes, they are 10. But there are some people who have diabetes and they also have what? Hypertension. So those who have both diseases, they are 4. They belong to the intersection. That's A intersection B. But those who have only diabetes, they are 6. They have diabetes, they don't have any other disease, or they don't have hypertension. They are 6. And when we get to B, the 8 involves those who have only hypertension. They don't have diabetes. They have only hypertension, or exactly hypertension. So they are 8. But those who have hypertension and at the same time they have diabetes, they are 4. So when we are counting hypertensive patients, we are going to count the 4 and add it to the 8 to make the 12. They are the hypertensive patients. But when we say those who have only hypertension, that means they have hypertension, they don't have any other disease. That one, we are referring to the 8. Now, if we are saying A are those who have diabetes, B, those who have hypertension, then we can say that the U is a set of patients, maybe in a particular hospital, a set of patients. And A is a set of patients who have diabetes. B is a set of patients who have hypertension or BP. So their intersection is there. So 6 plus 4 gives you 10. 4 plus 8 also gives you 12. Now the 2 we are seeing means that, mind you, the 2 can be anywhere. It can be at the top, it can be at the down, it can be at the side. It's just telling you that there are 2 patients in the hospital who did not have hypertension, nor did they have diabetes. But there are also patients in the hospital. Most likely they are battling malaria. But because this exercise involves only, what do you call it, diabetes and BP patients, that is why we demonstrate them or we illustrate them in the Venn diagram that we are seeing. Any question about this explanation before we move forward? Okay, if no question.
Please, I'll ask that you go over it again.
Hey, go over it, bye.
Yes, please. Because I didn't get it well.
They didn't get it well. That's
Yeah,
fine.
the 4, 8, 12, that's all. I wasn't getting it well.
Okay.
Hello, sir.
Okay. Yes.
Okay, so you made mention that the six, we should take it as the six belongs to those who have only diabetes but do not have hypertension, and
Yeah.
then the 4 belongs to those who have both disease, and
Mhm.
the 8 is the one who has only
I don't know whether
hypertension.
I'm struggling to hear you. Your voice keeps
I want to know the
going
other
low.
two, the 2 that is beneath, that does not belong to those class of disease. When you add up, does it mean that when you sum up all these figures, you should get the U20, the universal figure?
Exactly.
Does it always?
It's always like that. You're going to say something. The one who has a first question is that's his question. Explain the figures to you. Okay, all I'm saying is that the U is the total number of patients being considered. People are still entering. Total number of patients. And that total number of patients, when you add everything within the rectangle, it should give you that total number of patients. People are still late entering. Okay, so the 20 is a summation of all the figures, not those in brackets. When you add 20 and 2, sorry, you add 10 to 12, you are going to get 22. And that means there is a double count because the 4 here is counted in the 10. The same 4 is counted in the 12. So if you add 10 and 12, hoping to get 20, you are not. You are going to get a value that is bigger than the 20 because there is a double count of the 4. Now, so what I'm saying is that when you add a 6, the 6 is just representing the whole region here. The whole region 6, and the whole region 4, the whole region 8, plus the 2, you must get 20. If you don't get 20, there's something wrong somewhere you have to check for. 2. When we are seeing the 2 as a figure that is outside the A and outside the B, it's not always that you will have elements outside both. Sometimes you can add the figures within the regions represented by 6, 4, and 8, and it will give you the universal set. Just a minute. Let me lower that volume. All the patients are having, let's say this is diabetes and hypertension. So you realize that all the patients you are having, they all have diabetes and or hypertension. So the 2 outside there, no figure will be there. There will not be anything there, which tells you that when you add everything within the 2 range, the 6, 4, and 8, it should give you the universal set. That scenario is also there. When you solve a lot of problems, you see them.
Oh, sir. Please, if you'll be
Yeah.
able to set yourself well, I don't know, your network, the volume comes, then it goes down a little. It comes, then it goes down. So if you can be able to adjust yourself well.
This thing again. Is it better?
Yeah.
Yes, sir, we can hear you.
So I
Yes,
think
sir.
you should mute
Other
one of
machine is
your
giving us
devices.
feedback. Your other machine is giving us your feedback. Sorry.
I hope the echo has stopped.
Yeah.
Yes, sir, it's better.
Yes.
Yes, sir.
Great. Okay. So what can happen is that the 10 against the A could be represented by any alphabet, and you'll be asked to calculate for the A. All you have to do is to add a 6 to 4, and that gives you the 10. If it's the 12 that has disappeared, all you have to do is to add a 4 to 8, and that gives you what? The 12, because we are adding everything within that ring. We are adding everything there. Now, it's also possible we take away 6 and ask you to find what is represented in that region. So to get a 6, what do? We know that when you add 6 and 4, you are getting 10. So if 6 is not there, you just take 4 away from the 10 and you're having your 6. If it's 4 that is not there, maybe we represent it by Y. 6 from 10 will give you the 4, or 8 from 12 will give you the 4. So we can do all the gymnastics here. The most important thing is you should understand the concept. You should know who belongs where, and you'll be fine. It can also happen the 2 there will be represented by any alphabet, and you'll be asked to calculate the value of that alphabet. All you have to do is to add 6 to 4 and 8, and you subtract the sum from 20, and that gives you 18 from 20 will give you 2. I think that is perfect now. So let's look at how they are described. Number of everyone, that's the universal set, is 20. Number of those in A, they belong to A. That's why we are saying they have diabetes. They are 10. Number of those in B. So number of elements in B is 12. Those with hypertension. The number of those in A only, that's they belong to, they have only diabetes. They are only 6. Number of those in B only, that's they have only hypertension. They are 8. The number of those who belong to both A and B, that is what we call A intersection B, they are 4. They are 4. Now, number of those who do not belong to A nor B, that's A union B prime, they are 2. Then the next question, the next topic we are going to look at is what has been calculated, the probability of A. If a patient is chosen at random, what's the probability that the patient has diabetes? That is A. So you just divide the total number of those who have diabetes by the total number of patients you have. Then you have probability of a person having diabetes. Then when we ask what is the probability of selecting someone who belongs to only A, that is he has only diabetes. Only diabetes is different from diabetes. Diabetes means the door is open, the person can have diabetes and have other conditions. But diabetes only means the person has strictly diabetes, nothing else. That one, they are 6 out of the total number of patients, 20. When you divide it, whatever you get is the probability. We are going to look at probability, so don't disturb your brain for now. Iman, what's your question?
Please, I cannot see it. It's not showing at my end.
Is it a common problem or is the only one having that problem?
Yeah, please, he's the only one. I don't know.
I think
Bishop,
he's the only one. So
Tap
he
tap
can
on the
log
tap
out
on the
and
speakers.
log in again.
Tap on the
Pastor Iman, just
speakers.
log out and log in.
It's clear here.
Okay. Okay. Thank you.
Sometimes when you are using phone and you open a lot of apps, you have to close all the apps because some of them are working at the background, and their function may conflict with some of these things. Here we have a worked example. In a hospital, on a particular day, just one day, 100 patients visited the hospital. Out of the 100, 45 were diagnosed of malaria, and 60 were diagnosed of what? Hypertension. So we have 100 people, but we are talking about 45 and 60. So when you add 45 to 60, you are getting 105. Meanwhile, we were told that there are 100 patients. So once you are getting more than the universal set, here the universal set is what? Patients. Then the subsets are malaria patients and hypertension patients. So once it's more than the universal set 100, then it means some people are being counted twice. There is a double voting. So we have to look out for those people. Now, if 35 had malaria only and 50 had hypertension only. So when I'm saying only, you should know where they are belonging. Your brain should be telling you where they are belonging, even before we go to the diagram. Illustrate the information above on a Venn diagram. So Venn is the name of a person. It's the person who discovered this whole Meshach, you have a question?
No, please, I don't have a question, but I want our brother to help. Some of the students are behind; they can't enter.
Oh, okay.
But Kelly, please check on them, please.
Oh, no one is in the waiting room. Okay, one just came. Eunice. Okay. So, if 35 had malaria only, 50 had hypertension only, illustrate the whole information on the Venn diagram and find the number of patients who had both diseases. Find how many patients had none of the two diseases. How many patients had only malaria? How many patients had only hypertension? If a patient is chosen at random, find the probability that the patient had only one disease. So because this is a set, you have to define the various sets. Here we say the universal set is a set of patients. Then maybe we'll say M is a set of malaria patients. H, a set of hypertension patients. Then we move on. As you can see, this is how you do it. And when you do it like that, this also attracts what? Mark. Of what? Malaria. Yeah, 45 diagnosed of malaria and 60 diagnosed of what? Hypertension. So that is how you illustrate them. And we're told that there were 100 patients, and the 100 is there. So we have 45, we have the 60. So you look at the sentence and you see where each is represented. If 35 had malaria only and 50 had hypertension only, so see where they put the 35. If you are here, you belong only to M, that's malaria. You belong only to M. If you are here, you belong only to H, that's hypertension only. But if you are at where the X is, you belong to both M and at the same time H, because the two rings cover you. So, how do we get our X? You say you have your patients in the hospital. Maybe sometimes you use this to solve some financial conflict. They told you that, oh, there are 45 malaria patients and 60 hypertension patients. Then, you use your calculator. What do you call that one? That fee, how do you call it? Consultation. Consultation will be 45 plus 60. So that's 105. So each patient is supposed to pay 50 Ghana for consultation. So 50 times 105. Then the children are also telling you that no, what you are getting is too much. Let's see. 105. 10. That's fine. So I was saying that sometimes you have conflicts. Maybe in your consulting room, you saw 45 malaria patients and 60 hypertension cases. Then you did your calculation. 45 45 plus 60, you got 105, and you say consultation is 50 Ghana, so times 50, and you had 4,250. Meanwhile, your children are only accounting for what? 5,000 exactly. Then you are saying they have stolen you. You caught them. They are enemies of progress. Confusion, Basa. You just have to analyze the data you have. You analyze the data and you see things clearly, and you vindicate those who are vindicated. So here, there are actually 100 human beings. 35 are carrying malaria. 35 are carrying malaria only. 50 are carrying what? Hypertension only. And sometimes this is where they can also steal you. If they know that what you've been doing is you'll be adding the 35 to 50, and you get 85. You get 85. So you multiply your 50 Ghana, that's consultation fee, times 85. Then you are getting like 4,250. Then they have, out of your ignorance, made a profit of 750 Ghana cedis because you couldn't analyze your data well. So there are some people who are carrying the two diseases. You should be careful not to you should be careful not to ignore them, and you should be careful not to double count them. Then we also have why. The solution says, let U represent patients who visited the hospital. M represent malaria patients. H represent hypertension patients. X represent the number of patients who had both diseases. Take note of this thing very well. X is not a set, but it's just a number. X is a number of patients who had both diseases. So I'm not expecting you to put X in a curly bracket. Then Y represent the number of patients who had none of the two diseases. So that is where you put X, and that is where you put your Y. So without even going to the solution, you and I know that 35 plus X will give you 45. So what do you do to get your X? You just subtract 35 from 45, and that gives you 10. So your X is 10. Case closed. If you like, you can go this way too. We also know that X plus the 50 will give you 60. So to get your X, you take away 50 from the 60, and that gives you the same 10. So you have the value of your X. So the question that says, A pass illustrate the information on the Venn diagram. We have done that. Find the number of patients who had both diseases. That's X. Number of patients who had both diseases, X. So we calculated the X to be what? 10 patients. Then the C says find is it Christina Bar or what? Somebody raised their hand.
Yes, sir, it's me,
Okay.
Christiana
It's
Fernand.
Emmanuel. Some people are behind the door, so please help us.
Please, I
Someone
need
Okay.
says he's behind.
clarification.
Let's all try to be joining on time because I have to be moving from one tab to another tab back and forth. So
Then,
Please,
sir, please,
I suggest
in order
you.
not to worry, you can make me
Yeah,
the co-host. You can
exactly.
make me the co-host so that I'll help you with that.
this was very easy with Zoom, but you know Zoom has 40 minutes.
Yes.
But this one, I'm here to discover it. Maybe it should be my assignment. So that I will give it to the class reps. When they are coming, you do the admission. And when there is a ghost entering the class too, you can easily know.
Yes, sir. If not for time's sake, I'd have taken you through it.
I've actually not taken the first lecture we had. I tried doing it during the lecture, but it didn't work. So I'll work on it later. Yeah.
Okay, sir.
Now, question
Okay,
C: how many patients had none
Sir,
of the two diseases? Yes.
I haven't. Yeah, I said I need clarification
Okay.
on the event chart. Yeah. So the M 40, the 45 for the M, and then the 60 for the H. Where did we get that from? I'm a bit confused. If you can help me to understand that aspect. Thank you.
That's fine. Look at the question. Have you seen it? Have you seen it?
Yes,
Yes,
sir.
Yes,
please.
we've
I'm
seen
looking
it.
at it.
So the question told us that 45 had malaria and 60 had hypertension. And I was telling you that sometimes they may not give you the 45, and they will rather tell you the intersection. They will give you others and omit some, and that is what you are going to look for. So it's not always that the 45 will be given. It's not always that the X will not be given. The 45 can be omitted, X will be given, 35 will be given, and you'll be asked to find the 45. So you just add 35 to X and you get a 45. We can also vanish the 35 and give you X and the 45. All you do is to subtract X from 45 and you have your 35. So C, find how many patients had none of the two diseases. It means they don't belong to malaria ring, neither do they belong to the hypertension group. So they are outside. So is there, and we define those people as what? Their number should be represented by Y. So we put Y there. And how do we get Y? We know that when you add 35, you add X, you add 50, and you add Y, you are going to get 100. You are going to get 100. So we calculated X to be what? 10. So we add 10 to 35, that's 45, plus 50, that will give you 95, plus Y equals to 100. So 95 from 100 will give you the value of Y. So simple and straightforward. Okay,
Okay,
so
so a
therefore,
question.
ask.
Sir, a question,
Yes,
please.
ask.
Okay, so for the Y, may I add it? Please, can you go back small so that I can see the set? Okay. So for the Y, I added let me check on my this thing here. I added 65 plus 60
Where did you
plus
get a
Y
65 from?
equals
Where did you get a 65 from?
60. So I said I added 45 plus
You said
60
65. Okay.
plus Y equal to the universal set. And I still had 5 to be Y.
Okay. Let's look at it. 45 plus 60, what do we get?
Okay.
105.
So
105.
already you have exceeded the 100. We were told that there are 100 patients. So you have already exceeded the 100. I told you when you add a 45 and add a 60, you are doing double counting because X is included in the 45. The same X is included in what? 60. So if you do any gymnastic and you get the same answer, bear it in mind that It's just a mere coincidence, but it doesn't hold at all times. You can, however, take the 45. Once you take the 45, it means you are not going to use the 60. You will rather use 50. You are just saying that 35 plus x equals to 45. So when you use the 45, you are not going to use the 60. You rather use what? The 50 and add the y. Or you use 35 and use 60. When you use 60, you are telling us that x plus 50 is the 60. So you have no business with the x and the 50 again. So you just add 35 to 60 and add your y and equate it to 100 and make your y the subject.
Okay.
There are many ways of killing a cat. So this is the probability part of it. If a patient is chosen at random, find the probability that the patient had only one disease. So another question is, how many people had only one disease? We are not saying how many people had only malaria, how many people had only hypertension. We are only talking about disease, but the person had only one. So the 35 had only one disease. What disease is that? Malaria. 50 had only one disease. What disease is that? Hypertension. So how many people in all had only one disease? Then you tell us that 35 plus 50, that gives you 85. So 85 people had only one disease. Then when we ask you how many people had two diseases is the X. Because when you are at X, you have malaria, you have hypertension. So that's the two diseases. So probability that the person had only one disease is the total number of only one disease divided by the universal set. But we will soon go into the probability. So you have total number here, 85 out of the universal set, and that gives you 0.85. So that is the probability of somebody being chosen at random and the person having only one disease. It becomes a little more complex when the diseases are 3. But once you understand the 2-set problem, the 3 should be no problem for you at all. It's just a little transfer of knowledge. So here, we have P, Q, and R. The 15 against the Q is saying that when you add everything along or everything within that ring, you should be getting the 15. That is to add 6, 1, 5, and 3. 6 plus 5, 6 plus 1, that's 7. Plus 5 is 12. Plus 3, that gives you the 15. So if you add everything within that ring, you are getting 15. The 21 there means that when you add everything along the ring Q, or the oval Q, you should be getting the 21. So you want to add 3, 5, that gives you 8, plus 4, and that's 12, plus 9, and you have your 21. You have your 21. The R tells you that when you add everything within that oval or ring, you are going to get 17. Therefore, 1 plus 5 gives you 6. Plus 4, that's 10. Plus 7, and you have 17. So here too, when we ask you, we have 8 there. 8 tells you that if these are diseases, the 8 people there, they are sick people, they are patients, but they don't have any of the three diseases you are interested in. They also have their own disease. But because you are not interested in them, you are not creating any ring for them. So, when we ask you how many people have only one disease, you tell me 6 belongs to only P, 9 belongs to only Q, 7 belongs to only R. So these three, they have only one disease. And you add them, and that gives you 22, I think. 6 plus 7 is 13, plus 9, that will be 22. And when we ask you how many people have two diseases, exactly two diseases, yes, another technicality here, exactly two diseases. They have only two diseases. So the 3 there belongs to P and at the same time Q. So they have exactly two diseases. The one you are seeing there, they belong to P and at the same time R. So they have exactly two diseases, which are P and R. 4, they have also Q and R as their diseases. That's the only disease they also have. So they have exactly two diseases. So when we ask you how many people have exactly two diseases or two diseases only, you are going to add 1, 3, 4, and that gives you 8. 8 people had exactly two diseases. But mind you, the 5, they have 2 or more. So there is difference between how many people have two diseases and how many people have exactly two diseases. So when you are at 5, you have all 3 diseases. That means you have 1 disease, you have 2 diseases, you have 3 diseases. So when we say those who have at least 2 diseases come for a special medication, those with the 3 will also go because they have at least 2. But if you don't want to have anything doing with those who have 2, but you want exactly 3 diseases, then you go for the 5. The 5, they have all the 3 diseases. So you can describe them too differently. All the 5 diseases. Then the 8, they have none of the 3 diseases. None of the 3 diseases. So if 1 is not there and you have to find 1, you have at least 3 different ways of getting your 1. You can add 6, 3, 5 and subtract from 15. You get your 1. You can also add 5, 4, 7 and subtract from 17. You get your 1. You can add 6, 3, 5, 4, 7, 9 and 8 and subtract from 43. You still get your 1. You see that it's interesting. So to get the universal set, the total number of elements in the universal set, 43, we are adding 6, 3, 5, 1, 7, 4, 9, and 8. You are adding everything within the rectangle. And that gives you 43. If you add 15, 21, and 17, you are going to get a value that is far, far, far above the universal set. Why? Because you did double counting, you even did triple counting. You count 3 among the P. You count 3 also among the Q. You count 4 among the R and count it among the Q. You count 1 among the P and count it among the R. That makes it double counting. And the 5 is part of the 15. The same 5 is part of the 21. The same 5 is part of the 17. So if you add 15, 17, and 21, you have done double counting and triple counting. So it's not done like that. Emmanuel Bar, your hand is up.
Yes, sir. Sorry. We have to worry you again. Some people are still sitting there behind the door. So sorry.
Yeah,
Please,
I've just
have to
admitted
let
them.
them.
If you
Okay,
raise
thank you,
your
sir.
hand and I'm not calling you, you can just alert me by unmuting yourself, because the tabs
Okay,
are
sir. Thank
different.
you.
Yeah. So the same explanation, the same thing I've said, they are all here. So you have the P and Q only. The only is making the difference. P and Q only. Those who belong to P and Q only, they don't belong to R. They are 3. So those who belong to all the 3 are also there. Any question about this? You only need to do more exercises. You see the question, you define your you represent in Venn diagram, you ask any question, and you look for the answer from the diagram, and you are going. Any questions so far? If your hand
Hello,
is
my hand is up,
up,
sir.
okay, let's hear you.
Going back to the first diagram, when
Which one?
you were interpreting the first one with the first one we did, that is the malaria 45, hypertension 60, and Y was 5. Because when you were interpreting the people who had only one disease, you made mention of the malaria 35 and the hypertension 50, making 85. And my question have to do with the why. Where do they belong to? Thank you.
Good. So no much information is given about why. Nothing is told about the why. We don't have any information. All we know is there are also patients there, whether they have 1 disease, 2 diseases, or whatever, we don't know. But those that the information have been clearly stated, they are the one who used to answer the questions. It's possible malaria, your question is an excellent question. Malaria and hypertension. Then we saw other people there, but we didn't ask them what kind of disease they have, because our interest is not there. Our interest is based on malaria and hypertension. So it's possible this why people here, we say all malaria people should come here. People went, but the why didn't go. All hypertension come here. People went, but the why didn't go. But we still counted why as part of the patients of the hospital. So our analysis is based on one disease with respect to malaria and or hypertension only. Whether this one, they have yellow fever only, or they have typhoid and whatever, is no more our business. We don't have that information. We only know them to be patients. So we'll base our answer on those that we have the full information on.
Thank you, sir.
Pleasure. Any other? Okay. If no other question, The teacher is to do the easy one, and the students are to do the difficult one. What did I just say? Okay, I'll push the slides to the page, and we are changing the meter band to something else. Fif- 54.
50.
Oh, I'm seeing 54.
Yes, sir, we are 54.
Good. So, assuming out of these 54, we have 30 males and 24 females. 30 males and 24 females. Just take this explanation the way I'm going to do it, and you'll be good to go. So we have 54 human beings. Out of these 54 or 54 students, so you have occupied student spaces. Out of these 54, 30 of you occupy male space. You occupy a space that are males. Then 24 also occupy a female space. Then we say if one of you, if a student is chosen at random, what is the probability that the student is a male? Probability of a student being a male probability of the student being a male is simply calculated like this. How many males do we have? Then you tell me 30. How many students are there in the class? Then you tell me 54. So out of the 54 space, the male occupy 30 out of the 54. Thank you. So the males occupied 30 space out of the 54. And when you divide 30 by 54, you are getting 0.5555 recurring. So probability of choosing a male at random is 0.56. 0.56 or 56%. 56%. In other words, 56% of the students are males. 56% of the students are male. So probability of choosing a male is 56%. Then we ask, what is the probability of choosing a female at random? Then you tell me that, oh, it's 24 female students out of a total of 54 students. And that also gives you 0.44444 recurring. So 44, 0.44 is the probability of choosing a female at random. Or females occupy 44% of the student space in the classroom. So probability is as simple as I have explained. Let's look at some technical terms. So we have experiments. Experiments is an operation such that you cannot predetermine the outcome with certainty. You cannot be 100% sure that the outcome of this operation is like this. And it will always be like that. If it's like that, then it is not experiment. For instance, I'm sure you all have played Ludo before. If you throw a Ludo die, you are not sure. We have 1, 2, 3, 4, 5, and 6. You are not sure which number will surface. But you'll be shouting 6, 6, 6, 6 me Ludo, 6 me Ludo. It's just your expectation. The occurrence or non-occurrence of the 6 has nothing to do with the shouting or the calling of the 6. It occurs as it wants. But if you say, oh, you're going to get 6, anytime you say you are getting 6, the 6 comes. Anytime you say you are getting 5, the 5 comes. Anything you mention is coming. Then that operation is not an experiment. This is what we are saying. If you toss a coin has 2 faces. And we call one side the head, we call the other side the tail. Either the head will surface or the tail will surface. So, if you toss a coin, especially when they are going to play soccer, football, you realize that the referee will call the 2 captains to the center and ask them, which side of the coin do you choose? Which side do you choose? Then they will toss it. The side that surfaces is the side that wins. You cannot tell in advance that, oh, that the head is coming, and really the head will come. If it happens like that, it's not an experiment. So you cannot be certain with the outcomes. Now, drawing a card from a pack of cards, this one maybe the ladies will not know much about it, but of late some ladies have been playing cards too. And they say what a man can do, a woman can do, and even better. So they are also now trying to do everything. So if you toss a playing card, you toss it well. The one that will be on top, middle, or whichever position, you cannot tell it. You can't predetermine whatever, whether it's the king, the ace, or the 10, whether it's Kule, the heart, the diamond, or whatever. You can't tell in advance. If you are able to tell in advance and it always happens, then it is not an experiment, because for an experiment, you cannot predict with 100% assurance. Now, another term is what? A trial. This one, when we are solving questions, I will explain it to you better. But we are saying a trial is what? An experiment in a single performance of the experiment. No, this is not what. Okay. A trial of an experiment is a single performance of the experiment. So when we get to the examples, I will explain it to you better. Outcome is a result of an experiment. Outcome is the result of an experiment. Equally likely outcomes. In an experiment, the outcomes which have equal chance of occurring are called equally likely outcomes. For example, if we toss a coin has what? 2 sides, head or tail. Both sides have equally likely chances of occurring. So probability of it being a head is 1/2 because there are 2 faces. It's either head or tail. So probability of a head is 1/2. Probability of a tail is 1/2. Now, a Ludo die has 6 surfaces. A Ludo die has 6 surfaces, numbered 1, 2, 3, 4, 5, and 6. So there is only one out of the 6 numbers. There is only 1 out of the 6 numbers, and there is only 1 2 out of the 6 numbers. There is only 1 3 out of the 6, 1 4, 1 5, or 1 6 out of the 6. So they all have 1 chance out of the 6 chances of occurring. So they have what? Equally likely. They are equally likely um, events. But where we have a situation, one has maybe 1 out of 6 of occurring, and the other has 2 out of the 6, then they are not equally likely outcomes. Random sampling. Random sampling. So, when you have a population and you want to draw a sample from the population, and you are doing it so careful that you are not biased, then we say you have done a random. Your sampling is random, it's not biased, it doesn't have any bias. You are 54, and I ask you to go and call any 15 of your mates. Then you go and select those who are your friends, and you pack them and bring to me. You are biased. You are biased. So sampling is not random. Or you go because maybe I want to send them somewhere, I want them to do a small manual work. You decided to go and choose those who are your enemies and bring them to me. You are very biased. But when you do it in such a way that you are not biased, you don't have any favoritism against anybody, then we say you have done a random sampling. A random sampling. A typical example is maybe you decide to write everybody's name on a piece of paper. Then you put them together, you shuffle them, and you decided to put them in a box or a hat. Without looking at it, you decide to pick any of them. In this exercise, you have not expressed interest towards anybody, neither have you expressed interest or a bias selection against anybody. You are just being fair. Then we say your sampling technique is random. There is no bias. So, sample space is the set of all possible outcomes. All the possible outcomes in an experiment is a sample space. Let's say, for instance, if you toss a Ludo die, we are either going to see 1, 2, 3, 4, 5, or 6. We are not seeing anything apart from this. So we say your sample space is what? Is a set of 1, 2, 3, 4, 5, 6. There is nothing more, nothing less. If you miss one of them, then it's not the sample space for tossing a coin, a Ludo die. The sample space for tossing a coin is head or tail. If you toss a coin, you are not going to see anything apart from the head or tail. So the sample space for tossing a coin is head and tail. and it's always denoted by the letter S. That's why I highlighted it with yellow. Events. Event is what a collection of sample points in with a common property. So, for instance, we are talking about Ludo die, and we have the numbers 1, 2, 3, 4, 5, 6. Then I say I'm interested in even numbers. Even numbers. Then you tell me 2, 4, and 6. So they have a common property. The common property they have is what? They are all even numbers. We'll be using them. Once we are using them in the examples, you get the explanation better. Types of events. You have certain events. An event which contains all the sample space is a certain event. For instance, if in the tossing of a coin, and we are saying what is the probability of getting a head or a tail, these are the only possibilities. So here you are certain that either of them will occur. So the universal set is what? Head and tail. And that of a Ludo die is 1, 2, 3, 4, 5, 6. So as I'm saying all these things, we can relate them to the medical field and talk about your patients with the kind of diseases they will be presenting. A complement of a set, okay, impossible event is an event that cannot happen. So for instance, you are tossing a coin which has only head and tail, and I ask you what's the probability of getting a 6. You toss a coin, we are not expecting 6, so it's an impossible event. Or you toss a Ludo die, and you are asked what's the probability of getting a head or tail. That must be 0 because in tossing a Ludo die, we are not expecting a head, neither are we expecting a tail. Complement of an event. Complement, as the word means, is something you add to the set to make it a whole. So we just talk about even numbers when you toss a Ludo die. When you toss a Ludo die and you are interested in even numbers, then you are talking about either 2, 4, or 6. So those numbers that are left to make the whole thing complete, to make it the sample space, are 1, 3, and 5. So 1, 3, and 5 is a complement to the set that has the even numbers. It's a complement because when you add it to it, it becomes complete, it becomes full. And it's denoted by the bar sign on top of the alphabet representing the set. So if we say set A is a set of even numbers, then A complement is what? A bar. We can also call it A prime. That's A to the power 1. Compound events. When we are performing an experiment, or after performing the experiment, we are asking questions and we are using the word or the word and, we are making that event a compound one. It's like putting two or more events together. And the words that are normally used are the word and the word or. And in probability, for that matter set, when you hear the word or, it means you are adding. We'll be doing examples and you get these ones. When you see or, it means you are adding. If you see and, it means you are multiplying. This same thing, you can use the union, sorry, not universal set, union. When we say A union B, the union is representing or, which is also telling you that you are adding. When you see union, you are adding. But when you see intersection, A intersection B, you are multiplying. You are multiplying. So, once again, the word or, union, they tell you are adding. The word and intersection, they tell you that you are multiplying. So if you have A union B, it means either A or B. Either event A or event B, or both events occur. A intersection B means A and B occur together. A and B occur together. It's a little abstract for now. When we start solving the questions, you get it better. Mutually exclusive. Mutually exclusive. If two events cannot occur together, which we say they are mutually exclusive, they cannot occur together. There is no way you toss a Ludo die and you see 3 surfacing and you also see 6 surfacing. You will either see them, you always see them one after the other. At a point 3 will come, at a point the 6 will also come. But for you to toss a Ludo die and say, oh, both will occur together, is not possible. So when it happens like that, we say they are mutually exclusive. Mutually exclusive. But in a situation where they can occur together, there you can say that they are mutually inclusive. Independent events. If you have 2 events A and B such that the occurrence of A or the non-occurrence of A does not affect B, occurrence of A or non-occurrence of A will not affect the probability of B, we say that the probability, the event A is independent of the event B. It means they don't affect each other. Let me use a practical example to explain. For instance, if you have a sack, that has 2 blue balls and 3 green balls, making 5 balls in the sack. 2 blue balls and 3 green balls, making 5 balls in a sack. What is the probability of selecting a blue ball? The blue are 2. So if you select the blue ball, if you have to find probability of selecting a blue ball, that will be 2/5 because there are 2 blue balls out of 5 balls. So probability of selecting a blue ball is 2 out of 5. Now, probability of selecting a green ball is 3 out of 5. 3 out of 5. Now, assuming at the first experiment, a blue ball is chosen and they don't bring it back. If a blue ball is chosen and they don't bring it back, then the total number of balls that are left will be 4, with 1 blue ball and 3 green balls. So if you take 1 blue ball away, the total number of balls becomes 4, and you'll be left with 1 blue and 3 green. So when they now ask you, what's the probability of selecting a green ball again? You are left with 1 green ball out of 4. So the probability has changed to what? 1/4. Formerly, the blue balls were 2, and the total number of balls were 5. So we had 2/5. Now the green balls become 1, and the total number of balls becomes what? 4. So you have 1 out of 4. So the occurrence of blue in the first experiment has affected the occurrence of another blue in the second experiment. In the same vein, when the balls are 5, the green have probability of 3/5. 3/5. But when a blue ball is taken away, the total number of balls will reduce to 4. So the probability of a green ball now will become 3 out of 4, no more 5. So this tells you that the subsequent experiments the probability of the subsequent experiment are affected by the earlier experiments.
Great.
Yeah.
Yeah.
So the 2 events, one affecting the other, will make it dependent. So the one event depends on the previous event. That one makes it dependent event. But if the first experiment, nothing affects the subsequent experiment, then they are independent events. Sample space for experiments. Simple experiment involves performing an experiment once. Throwing a die once or tossing a coin once is a simple event. So we now find their sample space. So when you toss a coin, this one I said it already. When you toss a coin, the sample space is what? Either a head or a tail. If you toss a Ludo die, the sample space becomes 1, 2, 3, 4, 5, and 6. If you are to draw a card from a pack, the whole pack has 52 cards. So the sample space becomes 1 to 52. When you toss 2 coins, together, the story changes. When you toss one coin, we are expecting just a head or just a tail. But when you toss two coins together, what we are expecting to see is in the sets we are having there. Either the first coin will bring head and the second coin will also bring head, or the first coin will bring head, the second one will bring tail, or the first coin will bring tail and the second one will bring a head, or the two coins will bring you what? Tails. These are the only possibilities when you toss two coins together. Once again. Now, once again, tossing two coins together is the same as tossing a coin after the other. If you toss the first coin and toss the second one, what you are likely going to see is that the first coin brings heads, the second one also brings head. The first one brings head, the second one brings tail. Or the first one brings tail, the second one brings head. The first one brings tail, the second one also brings tail. These are the only possibilities when you toss two coins together. When you toss three coins, this is what we are going to see. Either the first will bring head, the second also bring head, the third also bring head. So you are going, all the three coins will be showing head, head, head. Or the first two will bring head and the third one will bring tail. Or the first and the last will bring you head, the second one will bring you tail. Or the first one will bring you head and the last two will bring you tail. Or the first one will bring you tail and the rest will bring you head. Or the first and the last will bring you tail and the second one will bring you head. Or the first two will bring you tail and the last one will bring you head. Or all of them will bring you tail. These are the options available when you toss three coins together, or you toss three coins one after the other. Then we have that kind of sample space. Sample space. Now, when you toss two Ludo die together, when you toss the two dice, maybe the first one we call it A, the second one we call it B. Either the first coin will bring 1, the second will bring 1, or the first will bring 1, the second will bring 2. The first will bring 1, the second will bring 3. 1, 4, 1, 5, 1, 6. Or the first will bring 2, the second will bring 1. So then we have 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 3, 1 in that order until it's possible the first die will bring 6 and the second die will also bring 6. These are the only possibilities when you toss two Ludo dice together. There is nothing more, nothing less. And this is a sample space for two Ludo dice being tossed together. Now, we are looking at you holding one coin and holding one die, and you want to toss them together. What are you likely going to see? The die has a sample space of 1, 2, 3, 4, 5, 6. And the coin has either head or tail. So when you toss the die and the Ludo die and the coin, either the coin brings head and the Ludo die will bring 1. Or the coin brings head, the Ludo will bring 2. Or head and 3, head and 4, head 5, head and 6. Or the coin brings tail, the die brings 1. The coin brings tail, the die brings 2. tail 3, tail 4, tail 5, or tail 6. These are the only possibilities when you toss a Ludo die and a coin, nothing more, nothing less. Now, we are approaching the calculation. As for the calculation, I have already said it. Probability of an event occurring is the number of the events divided by total number of what? The universe. So I'm saying that when you have an event, let's say the event of selecting an even number. So the question is, how many even numbers are there? That is the E. E is the even number. So how many even numbers are there? That will be the numerator. How many numbers are there in all? That's the denominator. And you are good to go. For example, if S or the sample space 1, 2, 3, 4, 5, 6, then the event that a number chosen from S is less than 3 is how many numbers are less than 3 from this set? We have 1 and 2 that are less than 3. So therefore, the probability of that a number chosen from S is less than 3 is what? 2 numbers less than 3 over 6 numbers. And that gives you 1 over 3 or 0.33333 recurring. Probability that a number chosen is greater than 2. So how many numbers are greater than 2? We have 3, 4, 5, and 6. So 4 numbers are greater than 2 out of 6 numbers. So we have 2 over 6. Probability that the number is divisible by 2. How many numbers are divisible by 2? We have 2 itself, we have 4, and we have 6. So there are 3 numbers that are divisible by 2 over total number of numbers, which is 6. And that gives you half, or 1 over 2. In fact, we can talk about a lot. Okay. Any questions so far? It's looking abstract, but worry not. You will get it. If notation, if E is an event, then probability of E is written P into bracket E. Probability of E is written P into bracket E. And that means that probability that E will occur. Probability that P will occur. And so the opposite is probability that E will not occur. And remember, we talk about complement. If E will not occur, then it's elements that are not part of E, and they are the complements we earlier talked about. So E prime or E bar is the event that E will not occur. And so probability of E not occurring is the number of elements that are not in E divided by the total number of elements in the universal set. The law of probability. The first and foremost law of probability is that no probability is less than 0, and no probability.
Yes, sir. Now we can
Yes.
hear you.
Yes, sir.
Oh,
Yes.
I didn't mute. Maybe the devil has passed around again. Okay. So, what I was trying to say is that no probability is less than 0 and no probability is more than 1. When you calculate any probability, the lowest number you can get is 0 and the highest number you can get is 1. If you get a probability less than 0, mark yourself wrong in advance. If you get any probability negative something, is wrong. If you get you calculate probability, you get 1.1, 1.2, 1. Even if you get 1.00001, the moment it's more than 1, it is wrong. The highest probability is 1 and the lowest probability is 0. The rest are all in between. And you get 0 if what the probability is talking about is not possible. For instance, the other time I made another example that we are 54 in the class. What's the probability of having a goat in the class? There is no goat in the class. So it's an impossible event. So it's 0 out of 54. And that still gives you 0. And that is the lowest probability. The highest probability. What's the probability that all of us here online, we are human beings? We are all human beings. There are 54 human beings online. So 54 divided by 54 is 1. So the highest probability is 1 or 100%. And the lowest probability is 0 or 0%. Forget about the proof. So probability of a sample space occurring is 1. So like I said, what is the probability that we are all human beings? All of us are human beings in the class. And so that is exactly the sample space. So sample space divided by sample space is 1. And that gives you 100%. And that is the highest probability. Probability of a null set. Probability of a null set or an empty set is always equal to 0. So if we define M as a set of goats in the class, M will remain empty set because there is no goat in the class. Or Y is a set of female lecturers online right now, unless we are told there is no female lecturer online. So it's an impossible event. So that one gives you 0 over 54. Now, probability of an event occurring plus probability of the same event not occurring is always equal to 1 or 100%. Probability that an event will occur plus the complement, that is the event will not occur, is equal to 1. For instance, probability of even numbers, when you toss a Ludo die, probability of even numbers is 2, 4, and 6. And that's 3 over 6. Probability that the number is not an even number is also 1, 3, and 5. And that's also 3 numbers out of 5. So probability of even number is 3 over 6. Probability of not even number is also 3 over 6. So when you add 3 over 6 to 3 over 6, you are having 3/6 plus 3/6. That gives you 6/6, which is 1 or 100%. So just bear it in mind that probability of an event occurring and probability that the event will not occur will give you 1 or 100%. So that is why you have seen in symbol. You have seen in symbol or notation. So probability that the event will not occur. So in that case, we can make anything the subject. We can make probability that the event will occur the subject. Lower the volume. We can also make probability that the event will not occur the subject. So we are saying probability that event will not occur is 1 minus probability that the event will occur. So if we say R represent probability that the event will occur, then probability that the event will not occur equals to 1 minus the R. And it can be proved, but the proof is not your business. Let's look at a practical example. If the probability that it will rain today or it will rain on a particular day is 0.41, then the probability that it will not rain is what? 1 minus 0.41, which is 0.59. You are told that probability that it will rain on a particular day, and that probability is 0.41. And you are now being asked to find the probability that it will not rain. And that should be what? 1 because we know that if we add probability of it will rain to probability of it will not rain, the answer is 1. So to get probability that it will not rain, we just subtract 0.41 from 1, and we have that. There's another probability there that it will rain tomorrow. That's 0.21. Then the probability that it will not rain will be 1 minus 0.21, which gives you 0.79. Any questions so far? We are now getting to the gymnastics. Any question? I hope I'm not online alone.
No, sir, you are not alone. We can hear you.
No, sir. No, sir. There's
Or
no
is it that you are
English.
confused or convinced?
Confused.
We are enjoying it.
But sir,
Wow.
I hope
Hey, sorry.
you are reading from the same slide.
Excuse me.
I said I hope you are reading from the same slide because initially I heard some 100 and something, but it wasn't in the slide.
You heard some.
You were giving an initial examples, but it wasn't in the slide.
Oh, I was referring to even numbers and odd numbers. I was just picking it from the previous example.
Oh, okay.
Now, you have your patients there. We have 45 malaria and 60 hypertension. That's what we did earlier. Yes, so they ask you what's the probability that a patient that will come to your hospital will be a malaria infected patient. You already have a data that predict that calculated malaria patients. So that data will help you predict for the future. So you say, oh, my hospital, the probability, anytime we have 20 patients, there is always about 10 of them who are malaria infected. So that is about half. Half of my patients are always malaria suspects. Then, based on that, we can say that, oh, when you have 70 patients, you are likely going to have like 35 of them being malaria infected. Okay. I wish I can give some. Okay, no worries. Let me see what I can do before I share this slide. A number is chosen at random from integers 5 to 25 inclusive. So in probability, we will tell you whether inclusive or non-inclusive. If they are silent or inclusive, then it means it's non-inclusive. But if they say it categorically, then it's inclusive. Inclusive means 5 itself is part of the numbers we are talking about, and 25 is also part of the numbers we are talking about. Find the probability that the number is a multiple of 3, the number is a multiple of 5. So we have S, integers from 5 to 25. We have 5, 6, 7, etc. up to 25. So how many of them are multiples of 3? Multiples of 3, we have 6, we have 9, we have 12, we have 15, 18, 21, and 24. So there are 7. Out of 25 numbers, we have 21 numbers. We have 7 that are multiples of 3. So it will give you 7 over 21, and that's 0.333 recurring.
12, 1, 2, 3, 4, 5, 6.
Multiples of 5. So what are the multiples of 5? We have 5, we have 10, we have 15, 20, 25. There are only 5 numbers that are multiples of 5 in that set. So 5 out of 21 gives you 0.2381. A number is chosen at random from the set S, which has 4, 7, 10, 5, 16, and 19. What is the probability that the number is even? The number is greater than 10. The number is odd number. The number is less than 10. The number is between 4 and 19. So we have this as our sample space, and number of sample space is 6. Then we have 4, 6, 10 as even numbers. 4, 6, 10. So there are 3 numbers that are even out of the 6 numbers. So probability of an even number is 3 out of 6, and that is 0.5 or half. So even numbers alone occupy half space. 1, 2, 3 out of 6. It means half of the space is going to even numbers, the other half elsewhere. The number will be greater than 10. So how many numbers are greater than 10 here? 13, 6, and 19. So there are 3 numbers. 3 numbers are greater than 10. And that gives you 3 out of 6. The number is less than 10. So where are the numbers less than 10? We have 4 and 2 that are less than 10. Excuse me, I'm running out of battery. So the number is greater than 10, and we have yeah, we did that one. Less than 10, we have 2 numbers. So the number is between 4 and 19. So we have 4, we have 19. How many numbers are in between? We have 7, 10, 13, and 16. So we have 4 numbers out of the 6 numbers that are between 4 and 19. Remember, they didn't say inclusive. If they say inclusive, then we will add the 4 and the 19. But they just say in between, or the number is between. So those numbers between the two numbers, 4 and 19, they are 4 out of 6 numbers. In a class of 20 boys and 30 girls, what is the probability that a student selected at random is a boy? So, mind you, this may not always be boys, can be number of polio. We have 20 polio boys or polio patients and 35 whatever. Always your mind should be like that. When you are seeing the boy, girl, they are all representing your patients, they are representing your staff. You can also conduct a search or a calculation or analyze the data on your staff. So total number of students in the class is what? 20 and 35 you add is 55. The number of boys in the class are 20. So probability that a boy is selected is 20 out of 55. And that reduces to what? 0.36. A bag contains 50 identical balls. 30 of the balls are green and the rest are red. Find the probability of picking at random a red ball from the bag. So the question is, how many red balls are there? How many balls are there in all? So total number of balls in the bag is 50. Number of red in the bag is what? 20. So the probability is what? 20 out of 50, and that gives you some 2/5. There comes a question. The first one is tossed twice. Write down the set of possible outcomes. What is the probability of obtaining exactly 2 heads? No head. At least 1 head. A head and a tail. So when a fair coin is tossed twice, the set of possible outcome is what you are seeing in green. The sample space is HHAT, TH, and TT. So you just define. Let the event E, let E denote the event of obtaining 2 heads. And then probability of 2 heads. So we ask, how many 2 heads are there? There is only 1 2 heads. The 2 heads, there is only ones that they occur. So that's going to be 1 out of 4. 1 out of 4. Probability of exactly 2 heads. Exactly 2 heads showing. So we have exactly 2 heads here. We don't have 2 heads here. We don't have 2 heads here. We have 2 tails here. So probability of exactly 2 heads is also 1 out of 4. 1 out of 4. Probability of no head. This thing, they are always interchangeable. Instead of saying probability of 2 tails, we are saying probability of what? No heads. It means we when the 2 coins are tossed, there's no head occurring. So the first one, 2 heads are there. The second one, 1 head, 1 tail. The third one, 1 tail, 1 head. The last one, 2 tails. There is no head there. 2 tails. So probability of no head is what? 1 out of 4. Then probability of obtaining at least 1 head. So at least 1 head means 1 or more heads. We've been using that phrase, at least, but we actually don't understand what we've been saying. We only use it to garnish the English we are speaking and without being careful about what exactly it means. When you have at least, it means you are saying minimum, that's the minimum. So there is a maximum too. So we also have at most. So at least 1 head. Here there is a head. Here too there is a head. Here too there is a head. But the last one, there is no head. So at least 1 head means 1 or more heads. Therefore, we have 1, we have 2, we have 3. Probability of at least 1 head is 3 out of 4. 3 out of 4. Probability of at least 1 head is 3 out of 4. A head and a tail. Probability of getting a head and a tail. So here there is head. Here there is head, there is tail. Here there is head, there is tail. Here, tail. So a head and a tail. We have here head and tail. We also have here head and tail. So a head and tail, we have 2 out of 4. 2 out of 4. So the probability is half, 0.5, or 50%. Probability of 2 heads, that's quarter, and it was 0.25. And all that I have said, they are all here. Probability of no head. So so we denote the events by F, which means the event of no head. Okay, I think we are on course. Any questions so far? Yep.
Yeah, so
We are enjoying it, sir.
Thank God.
we are enjoying it, sir.
My hand.
Mr. Kumsin, please.
Same as tossing 2 coins once. So you always remember
Sir, I
that.
have a question on that. Sir, I've raised my hand.
Oh, okay. I'm not on that one.
Okay. So you are doing a similar one. I am coming to ask of if the coin is tossed thrice.
Okay.
1 second. 1 second. I'm for you.
So if we were to be meeting in person, that would have been your question. I have done 1 for you, I have done 2 for you. Then I want to tease your brain. I want to tease your brain with the 3 coins. The moment you are able to do it, then the smaller ones will be easy for you. Okay, so we have 3 fair coins tossed once. So when we say 3 fair coins are tossed once, it's the same as tossing 1 coins 3 times. Write down the set of possible outcomes. That's the sample space. What is the probability of obtaining exactly 2 heads, no tail, not more than 1 head? So when 3 coins are tossed together, these are the possibilities. We already talked about it earlier. So the number of the sample space is 8. There are 8 options here. 8 options. So the first part is a sample space. We have done it. What is the probability of obtaining exactly 2 heads? So where do we have exactly 2 heads? All the yellow ones are exactly 2 heads. We don't have less than 2 heads. We don't have more than 2 heads. We have exactly 2 heads. So probability of exactly 2 heads is 1, 2, 3 out of 8. Probability of exactly 2 heads is 3 out of 8. So the 3 are the yellows out of 8. Probability of no tail. There is only one instance that there is no tail. All the rest, they have tail. They have at least 1 tail.
So my hand is up.
Okay, that's fine. We are listening.
Okay, sir, thank you very much. What I want to ask is that always when you convert everything, the last mark is always converted into decimal fraction. And I would like to ask that should we always convert the final exam to final answer to decimals? Because all that almost everyone of them have been converted to decimals. Like 1/3 is 0.333. 4/11, 0.2. That's what I'm asking. Thank you very much.
That's fine. Thank you too. So if the question is silent on how your answer should be, any of them that you leave your answer in will be marked correct. If the question just asks you, what's the probability of blah, 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 you can do your calculation and leave the answer in fraction. You can do it and leave it in decimal. You can do it and leave it in what? Percentage. They are all correct.
Okay, thank you very much.
Sometimes the question will tell you, leaving your answer in 2 decimal places. So if it's 2 decimal places, then this will become 0.38. Then probability of no tail. Okay. We did no tail already. Not more than 1 head. Not more than 1 head. So here the hairs are more than 1. Here too the hairs are more than 1. The hairs are more than 1. Here the head is 1. Here too the hairs are more than 1. The head is 1. The head is 1. No head. Not more than 1 head. So it's a very humble exercise. Not more than 1 head. Here more than 1 head. Here more than 1 head. Here more than one head. More than one head. So the rest 1, 2, 3, 4. No, not more than one head. So it's inclusive.
Yes,
So
we
you have
have 3.
4 out of 8.
We have
We have one head. They are saying not more than, which means one or less. One or less, not more. One or less. So we have
3, 4.
this, we have this, we have this, and we have this. So that gives you a total of 4 out of 8. Any questions so far?
Sir, my hand is up.
Okay, let's hear you.
Okay, so I just want to find out if it is possible to close earlier today because my brain is no more absorbing at all. I don't know about my colleagues. Thank you.
Is that a question?
So those are not good.
Yes, it's a question. I
That's
said,
your
is
question.
it possible? Yes, thank you.
This suggestion.
Looks
This
improbable.
With
Okay,
a
so
lot of it.
we had about 4 classes earlier. How many of them did we close earlier? So calculate the probability of we closing earlier today.
Hey, bayo. Ayata.
Thank you.
You see that?
So this one dear. This one dear, sir. It's not easy.
It's not easy, eh? It's not easy. We have just done the gymnastics. We had 4 classes earlier. How many of them did we close on time? How many of them did we close earlier than time? How many of them did we close after time? If you have this statistics, you can easily calculate the probability and say, oh, today I can predict him. He will close on time. Oh, he will not close on time.
But this one is mathematics, so it's pulling our brains, Papa.
I hear people.
Concentration is 100%, but absorption is reducing.
It's reduced,
Not
to
reducing, but
0.3.
completely reduced.
Yes, to 0.1.
Wow. Yes, any other question? That question will be the last to be answered.
Yes, Lord.
Okay.
I want to ask the question.
Ask.
If you are giving 3 coins to toast, will you be giving the permutation, the head, and the head tail? Will you be giving that permutation in the brackets, or we have to do the permutation and come out with all the possible outcome and then do the probability?
Not at all. Nobody will give you. You can only see, even in objective, you may not be given. You have to
then you
be
have
able to tell that.
come out with the possible outcome.
Exactly.
Okay.
3 coins. Okay. It's possible all of them will bring heads. If you do it well, you don't do it randomly. Look at it. Head. Then you take away the last head. Head, tail. Then you now take away the middle head. Head, tail, head. Then you now introduce a second tail. Head, tail. Then you now introduce 2 head. Tail, head. Then, I mean, it forms a pattern, interesting pattern that you can always remember. You can also rearrange it the way you want. It doesn't mean that you should always bring the head. You can also start with your tail. There's nothing wrong with it. Even the Ludo die we ditch. Where is it? Yeah, you can decide to start with your 6, 5, 4, 3, 2, 1. 6, 5, 4, 3, 2. You will get the same answer, provided your arrangement is correct. Any other question?
So, Doc, is this type of examination going to be like an aptitude test, or I mean, why are we doing it?
Hey, probably.
So, this question again. This question again.
The question is, I'm
asking. No, I know. I hear you. I'm asking that this question has come again. Somebody should answer that question.
Only God can tell. But we will answer it. Waiting and objects.
Meanwhile, you are owing me one assignment too. You said this week Friday. You think the Friday will never come? It has come. The question is already in the slides I gave. I hope you are aware. Oh, you have forgotten.
So what did you say?
Forgotten.
I think so. We've forgotten. Did you say we are writing an exam?
What is going on Friday?
Hey!
we are not aware.
Assignment. Yeah, I remember assignment. Okay.
Mr. Ban, you don't remember anything, please.
Okay. You and I were there. I was going to say last week Friday, and I ended up saying next week Friday. And you pleaded that it should be next week Friday. We have entered the next week. And the Friday is closed. You have forgotten.
Charlie.
Hey, but I thought that
So is it an assignment?
I
Is it an assignment that is to be submitted?
I thought we did it.
Of course, yes.
Hey.
Then Mr. Ban, where's the pink sheet?
Please, if you can be supported, we will be glad. Please,
Please, can we have the question again on the page so we look at it?
Yes, I'm sending it. I'm sending it.
Yeah,
I want to ask
the pressure is just too much on us, so we get confused.
Sorry, it will soon become hey people, I'm looking for it. It's on the slide. The slide is on the page.
Sepis have posted a screenshot. I don't know if that is it.
Let me check. Perfect. It's exactly so. Okay, refer them to the page, the slide number. It's in the slides. The one who is saying nothing is happening on Friday.
Page 78.
Yo. This means that when I gave you the slide, nobody went to go through.
So we went through, but we forgot the assignment. After that one day, that is the truth. We forgot the assignment.
Hey, if I were to say we are writing a quiz today, you would have read everything.
Sir, the truth of the matter is that on a daily basis, there's a class. And here's the case, we are also workers. So we barely don't even have the time to go and revise. That's the problem. On a daily basis, sometimes 2 lectures. And you close at 10, so you can imagine. You work, you go to school. So we don't have like a day off, 2 days off where you can sit down to say, okay, let me go through, my slide on what we were taught. You don't even get a time. So it hasn't been easy for us. So please continue to bear with us. Thank you so much.
And so exactly Friday timetable is another difficult one.
I didn't say work it on Friday. I gave you almost 2 weeks. I didn't say work it on Friday. You had it to submit coming Friday. I was going to say last week Friday, and I ended up saying next week Friday. And I remember I told you that the previous class, one of the previous classes, we're having the lecture 5:30 a.m. to 8 a.m. Yes. They all said that was the time okay for them. I said no problem. It's fine by me too. So by 5 a.m. I share the links. By 5:30, we start. And by 8 a.m. we are done and gone. Don't worry, it is well. You'll be fine. You have a story to tell one day.
We shall overcome.
Yes, deep in your heart, you do believe that. Okay. We just have 18 minutes. We'll continue the probability next week. I hope we'll finish that one too. So next week, do you write a quiz?
Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
Yes. Yes, please.
Yes,
Give us an
accepted.
Yo, I hear. Even if somebody says no, I told you we are writing 6 quizzes. So the 6 will surely happen. So the earlier we do it, the better. Otherwise, they will pile on each other. Maybe you end up having them every other day, and you come and tell me that your brain wants to burst in your head.
So which areas should we concentrate? Which areas will it cover? So we can revise, please.
So me, I'm always flexible. Should I take it from the very beginning, or I should take it after the second quiz, after the first quiz?
After the first quiz.
Yep, after the first
quiz. Yes, after the first quiz.
That will be done. That will be done. There's no problem at all. Okay. Any other question?
Yes. Someone is asking, that is the assignment individual or group assignment, the one that you gave us.
So you are not even close to each other. If we say group, one person will go and do it and write others' name on the sheets that's the group, or you submit. So do it individually. If we're to be meeting physically, you are all together, then I can have some probability that majority will take part. Everybody will definitely not take part from the beginning to the end. You start it, somebody will stop along the line. He will tell you that, he has emergency. And the rest will do it and they will add his name. So it's a practice. Don't worry. Just do it and submit. It's not.
So we have been doing group work on our
Are you
group.
going to write it or going to type it?
You can handwrite it. Okay, that's a very good reminder. So I posted my everything on the page. You can do it. Take a shot of it and send it to me by email or by WhatsApp.
Okay.
Don't put it on the page.
Okay.
Do not post it on the page. Send it to me individually. I think email will be better. Let's not send it by email. If you do a PDF, I'm fine. If you don't do a PDF, you can send it by JPEG. There's no problem. Anything we can talk about again?
Sir, please, may I find out?
Excuse me.
Hello, sir.
Yeah.
Yeah, the assignments you are talking of, is it the standard deviation and variance?
It's on the
Or
page.
it's a different
They
one?
just
It's on the
posted it
page.
on the page. And I was told that
Okay,
the
thank
slide
you.
number is 70.
Thank you, sir.
Okay.
It is a pleasure. Okay, if no other question, then we can end it here today. We call it a
Thank
day
you, sir. Thank you, sir.
and see you on Tuesday with a quiz of maximum 20 minutes.